Okay, I got the permission. Yeah, okay, you're recording. Very good. Okay, let me start over. So here we go. So we started on forces, hydrostatic. We showed that actually hydrostatic, even though the fluid is not moving, is part of fluid mechanics. We tried to show basically how forces are created as a result of pressure distribution. And we looked at pressure on flat plate. We didn't make it too complicated. We tried to make it as simple as possible. Center of pressure, things like that, which are very, very important. We showed how it is done on a flat surface. Again, we're trying to teach the principles. We're not going to too much complicated geometries. Hopefully you understand the concept. And then we started with buoyancy, which is Archimedes' laws, and he figured that one out 2,000 years ago, so it's not too complicated. And the plan today is to finish that one, get back to what we started with, the one-dimensional flow, which are kind of examples on typical of conservation of mass and momentum. But we're also going to add the Bernoulli equation, which is pretty well-known and famous, but it has some limitations. So we'll try to emphasize that again, and so on. Now, some students were kind of nervous. They didn't know where the first midterm exam is. So let's make them happy. Okay, so let's do that. So what I will do is I will put here a calendar, and I would think it's going to be next month. How about that? I think it's next month sometimes. Let me get October up here. Okay, let me stop share. And another thing I wanted to say, one or two students told me that when I go through my notes here, and I'm using PowerPoint, that's the way I'm doing it, I'm going a bit too fast. And I just want to hear more opinion, but let's finish up that thing in a minute. And okay, share, and this one, share that. Okay, did it work? You see the calendar? No.
Yeah.
Yes.
Yes. See it perfectly well, Professor.
Yes.
Yes.
You see that at my end, it didn't put, usually it puts a green kind of peripheral thing on. Okay, as long as you can see the calendar, this is next month, October. I was thinking that anywhere from the 6th to the 22, maybe. So how do you going to do the vote? One option is you try to do the thumb up, but let's see if I can see that. How are we gonna do that? Okay, so anybody does a thumb up? Can I see that or? Okay, let me, can you unmute yourself? Unmute yourself. How about the 6th?
Professor, we can just annotate the screen if you want.
Can you?
Yeah, we can just annotate the screen and put like a dot on the day we prefer.
You think so?
Yeah, here, I'll show you.
Oh, there's a, okay, I see the annotate, okay. Annotate.
I drew that, Professor. I'm the little line on the 15th. That's
I never used that. Okay, I never used that. So put a line, good, good. So, and there's a raising.
Like a tally mark.
Okay, we work it out. Good, good, good. Redo clear. Okay, I've seen all the tools.
I wonder which one.
It looks like the 15 is becoming popular.
I'm a trendsetter.
What is that? This is objection or this is approval?
I don't know. What is that? Why did someone do that?
I guess the 15th then.
I guess the 15th.
How's everyone doing now? I'm not able to put a line.
Okay,
If you go to the top where it says view options, there's a drop down menu and then click annotate.
You're awesome, Fatima.
It is a bit laggy as well.
Oh no, this guy's nervous. Who is this? He's very nervous.
Oh, you did that.
Whoever did that, you
Yeah,
should
that
be.
doesn't matter as long as it's kind of focused around the date, which is the 15th.
It definitely seems to be focused around the
30 is a
15th.
Friday. If somebody looking for Friday,
Professor,
Okay,
quick question. If we had the exam on a lecture day, would it take place of the lecture or we would still have lecture that day?
what will be the material on the exam?
No, Professor, I'm asking, will we still have lecture if we have a test on the same day of lecture?
Oh, you wanna say you don't wanna lose too many hours. We're conducting it exactly as the in-class teaching. So that particular day, instead of actually the university policy is very strict about it. We have to do it at the same time slot.
Okay.
Can we do a poll, please?
Okay, I think there is a very solid thing here. I would think that we're talking about the 15th.
Well, Professor, there are also unheard opinions of the 22nd, but I'm not sure. I believe
Yeah,
there
can we
is-
do a poll or something?
I believe there is a poll option that we can do.
Because I can't even annotate anything because I can't see.
Okay, you guys wanna, okay, so very clear to me at this point that it is the 15th, but some of you are really trying to promote the 22nd. Can we do a repeat with just those two dates? Do you agree? Okay.
Yes. Yeah, I approve.
Okay, stop share.
Yes.
Let me do that. Stop share. And
Professor,
then,
maybe we could not draw on the screen this time. I know that there's an option to send us the option of just those two dates.
just give me a second. Okay, let's finish this one in calendar. Okay, now. I think now I got the full calendar. Okay, now I got it right. I think before I got the whole screen. Here we go. So just do on that. Either 15 or 22, but try to do little lines, small lines, or stars or whatever you wish.
Who put on the 5th?
Well, we're gonna have two exams then.
Professor, I feel like
Yeah, I
this is more
think
complicated
this is
than
definitely
it should
more-
be.
Professor, there's a poll option on.
Yeah, can we do the poll
There's
instead?
definitely people
It lets,
voting more than
lets
once.
students vote, and then it counts which one has more. Because students are voting more than one.
Yeah, unfortunately, people seem to be spamming.
We can.
Yeah, someone voted Halloween.
It seems
So
like the
far,
15th.
15 is the winner. 15 is winning.
Well, if whoever knows how to do the poll option, can they explain it to the professor so he can send it to us?
Okay, just. Are we still voting or is it done?
Jeez.
I don't think this is a valid vote.
Someone's just. spamming.
Someone's continuously just spamming stamps.
I can go Google how to do it, and then we can do it at the end of class, maybe. So, I don't know.
That might be good.
But
It's like a good idea.
it does
can
seem
just-
to be tied between 15th and 22nd, though.
Yeah, we can just vote
We can
between
all
those
do
two.
the raise hand, the clicking yes, and then we just assign which date to each one, and then he can just count how many of them there.
Let's make it short. Okay, it looks like the 15 is date. So let's do it on the 15th. Finish, end up.
Sounds good to me.
Okay, Professor.
Okay, on the
Sorry.
15th, let me just
Good
make a
one,
note for
everybody.
myself.
Yeah, somebody put how to do the poll on the chat.
So somebody's a criminal over there? Yeah. Okay, so, you know, we'll take the 15th. Okay. Exam, October 15, exam number 1. And that's
Someone
it.
put how to
Guys, we can spend the whole hour on this, and then we're gonna. There was one student who was concerned about the time, so we're gonna lose one lecture. So, all right, I'll stop it. That's it. Gentlemen, ladies,
Excuse me, Professor?
it is gonna be on the 15th.
What time?
Exactly when the class is, 4 o'clock, and then 5:15. We'll see. We can plan on 1 hour, and then maybe I let you go 15 minutes beyond or something like that. It's going to be very similar to the examples I'm doing. It's not going to be too difficult. I just want to bounce back something with you guys for a moment. When we in class in normal times, what we do is I have a whiteboard. I write, or I write on the little white pad on the desk, and it goes on the projector. So basically, what happens is I develop and write the equation in real time, and you have more time to see line by line and more follow me. I would say so. Okay. The other approach is to have a PowerPoint, which is pre-prepared, and I just talk and explain, and then maybe put an arrow, and this way usually we go faster, and your chances of following the professors are less, not as good. In that situation, I decided to follow the PowerPoint approach, and also you have a book, and also I'm posting a result or summary of the lecture each time. I'm not sure which is better, and I'm not sure how other professors do that. That's another problem, that we're not really following each other. But I asked for the department to provide me with this board. They say they can figure out something that I can try in the future to do a class which will be very similar to what I would do in a face-to-face operation. So maybe 1 or 2 students, if they can make a remark, and then we go on, because we already lost a few minutes. What do you think about that approach, or any preferences about the 2 methods?
It sounds pretty cool, Professor. I personally don't mind it at all.
Okay, so if I get the equipment, probably in a week or 2 weeks, I don't know how fast the university operates. We'll make an experiment, see which one you like more. Okay, so at this point, we agreed that we're going to have a first exam on the 15th. Again, chapter 2 was very, very mathematical, and I want you just to remember the concept and all that. Then we went to this one, which is the hydrostatic. I want you to be able to solve the cases I'm doing, okay? Very simple, they're not complicated, but I'm not gonna ask you to do some complicated integrals and all that. And I mentioned several times, this is not the math course, this is fluid mechanics. So I'm trying to teach you the physics, the principles. And if you follow me, you'll see later on that that's how it's gonna be. Anyway, this was a little bit of speech, but let's go to business and start working. Okay, so we tried to finish this chapter. Yes.
Is the midterm going to cover every chapter that we cover until the 15th, or will it stop like a week before, or which chapters are going to be covered?
Typically, my answer is, in any situation, is that you have to understand everything to the last lecture. However, my intention is not to really create any problems, and usually it will cover topics that been covered in the homework. So it's kind of a 1 week behind or before. Okay? All right.
you.
When we get to the exam, get closer, you'll see, you'll get lots more information and we'll specify things very, very clearly.
Professor, one last thing, Professor.
Go ahead.
I think that the biggest thing with the lectures and all that is when we go over the examples, I think it would be much more beneficial for everybody if we see you, if we can just watch you do the example from scratch instead of seeing everything up there and then you explaining it. So when you get the materials you need, is there a way that we can do that? Like when you explain, we do the lecture, and then when you show us the example, we can just you can just do it from scratch and we can watch you and see in real time.
You're in favor of what I was mentioning before. If I have the equipment, we'll do it, and you're probably gonna like it. Because
okay, perfect.
And if you follow me, again, the old philosophy is that if you take your pen and you try to write down your own notes, then you're really learning. And this way, I agree, it's more difficult. But again, we are not in normal times right now. So, and I don't know what the other professors are doing, which is a kind of pity that we don't interact with each other. But I think most of them are probably using PowerPoint or something like that. Anyway, this is what I have. So you guys are with me, and we'll try to make it as workable as possible.
Professor, I have a question.
All right, let's move on.
So about the exam, are you gonna provide the formula, or is gonna be like needed formula next to each question, or how is gonna be?
Okay, how about we do an example and then you ask in between the examples, okay? We're gonna do examples in a minute, okay? Okay. Stay and watch me when I do that, okay? It's Ariba, right?
Yes.
Okay, all right, thanks for asking. All right, so let's do full screen. Okay, I'll go full screen now in teaching mode. That was number one, and let's go here. So this is a quick summary. Okay, so one more time, we try to learn about the effect of pressure, how the force is generated by the pressure, and what is the center of, excuse me, center of gravity. I did the integrals and all that. At the end of the day, we developed some formula or some procedure. And I said, okay, look at the centroid of the area.
Professor, we can't see the screen. I'm sorry.
Oh, you're not full screen yet. Full screen, then I need the pen. Okay, so this is a quick summary. So I did the integrals.
Professor, you need to share the screen first, please. We're only seeing you right now.
You cannot see the screen?
Yeah, we only see you right now.
Yeah, you had stopped sharing.
Oh, that's not good. Something happened? Okay, you can only see me, and I'm waving my hand. Let me start over because I started having computers. Anyway, the university is trying to shut down my email because I didn't renew the password. So I'm trying to be careful. All right, so let me do again. Share. This way. You see that?
Yes.
Yes, Professor.
Okay, now I go full screen. Still with me?
Excellent.
Yeah. Yes,
Okay.
Professor.
Okay, big success. All right. So for those that are afraid of integrals, I did the integrals to show you how it is done. And then we ended up with the procedure of how to work it. And here, this is the procedure. I showed it several times. I show it again. This would be a procedure. I usually end up doing that. So the procedure in this particular case, you have a pool, you have a shape, you have to put the coordinate system here. Once you put the coordinate system, then you try to figure out where is the centroid of that particular area, which is here. I did it several times in the past. This will be the centroid. You find what is the depth of that point. Then you find the average pressure at that point. Then the force is multiplied by the area. And then you have to go to the tables for the moments of inertia, the XY. If it's symmetric, if this object is symmetric, left and right, if it's a symmetric, completely left, I don't know how my drawing is good, but if it would be symmetric, then this is 0. If it's not, then we have the tables. I'm going to use only simple configuration which are here. Most likely we're going to use, I touched the, let's see, I'm not supposed to touch it. Most likely I will use these. So this is, I mentioned that before. This is what I'm going to use. These are also simple, but it's too much algebra. Okay, I'm going to save you from that. Then, this one I'm usually not going to use for curved surfaces, but this is a remark that if you're going to hit a situation when you need to come up with quick calculation about the forces, so suppose on a curved surface, then you can just simply take the weight of the liquid above that. That's going to be the force, which is that direction. If you want to find out what is the force that direction, then you can have the projection. And then the pressure distribution looks like that. Okay. Looks like this. Okay, I don't want to spend too much time. It's centroid of this area. And then the force to this direction is going to be probably the average pressure at that particular point. And that's very simple. Otherwise, you have to do integrals on curved surfaces, and then you're going to get scared. Okay. Well, I have to close my phone because I have all kind of things coming at me. All right. Now, buoyancy. We started buoyancy, and we mentioned Mr. Archimedes, who ran in the street of Syracuse in Sicily, and with his towel or without, nobody remembers. And he said that the buoyancy force equal to the weight of the displaced liquid. It's okay for floating object, for submerged object. And he also said, which is more important, that the buoyancy acts through the centroid of the area. This one is not obvious, so we need to prove that one. Then I went through quickly, and I showed you that we can prove the laws of buoyancy by simply looking at this one here. One more time, pen. At the end of the day, we ended up with this thing. So we looked at the forces on the upper surface, on the lower surface, and ended up that the lift is equal to the weight of the displaced liquid. Okay, we did it last time, you know that from high school. Then we tried to incorporate what you know from mathematics, and of course all of you are expert after you took calculus. And there is Gauss theorem, and we basically wanted to do the surface pressure integral. We want to do this one, but turns out that he is helping out. Instead of that, we can do the volume. We convert the volume, which is the gradient P is only to the G direction. We put it in, comes out very simplistically, exactly the same result. So, okay, we proved that. We used big power tools and simple tools, same thing. We did it last time, so I'm just saying. Okay, so here's end of class. Okay, so now we move to new territory, and we're trying to prove that, hey, this is actually, the force is acting through the centroid. So let's say, so what we do is, let me get the pen. It's the same process we did before when we tried to figure out the averages. So we take a coordinate system, and then we have slices. We have slices, which are going to be now dx, or actually dv, basically, if it's multiplied by the area, and then the x of that. And then we keep on integrating, adding all them up. So we're saying there's some kind of a magical point, which is x of the center of pressure, times the total, the sum of all that lift. And then we have to integrate this segment, the lift of this component, and then of that slice, of that slice. And that's the same thing, which is find the center of gravity or something like that. But we're trying to come up here. So here's the XCG, which we're trying to find. And then the lift, we already saw that the lift is the volume of the weight of the displaced liquid. And then the other side integral is dl, actually. So we just put it in here. Okay, so it's going to be a local x, integral of local x and dv and rho g. We cancel out that one, and we end up with this. So we just simply divide it by x dv, and we end up with this. So now, this is exactly the formula for the centroid that we had before. Okay, but now it's in terms of volume. And the same way for the other component when we try to integrate this way, the slices this way. Okay, so we did those algebras and we ended up, yeah, he was right. Those forces act through the centroid of the volume. Okay, you know that, I went through quickly all that. Okay, so that's all we need to know. Okay, so now we're ready for examples, So let's see, so those students that ask a question, how's the exam holder? So I would expect you to solve problems like this based on what we studied, okay? So here is the very I'll start simple and go a bit more complicated. So here's a cylinder, has no weight, and has the dimensions, 0.4 meter wide, and the diameter and the height is 0.7. And then we're gonna put some weight on it, which is 25 kilograms, and we wanna see how deep it will sink because of that. Okay, so initially it's up here. It's up here like that. And now we're putting the weight and it sinks to a depth. So we think that the volume which was displaced is times the density or the weight of this displaced liquid must be equal to the weight of that thing, okay? So rho GV, we say rho GV, but V is actually pi r squared must be equal to the weight of the weight that we added. So let's see. So here I solved the weight equal to the volume. Oh, and then I forgot to put here H. So we need to find H actually. And so we put it here, okay, the volume. And I did step one, just find the volume because we know the weight and then we know rho G. And therefore the volume is pi r squared. This is r squared. And times L. So I put the L here, divide the volume by this, and I end up with this quantity, which is H. Very simple. Anybody say hi?
Professor, so the L there, is that supposed to be an H where it equals volume over pi times 0.2 squared?
Yeah, I can rewrite it. I wrote it this way. Okay, so let me do it again. So the way I would like to say is that the weight is equal to the displaced volume, rho of the weight, rho G and volume. Rho G, and it's pi r squared times H. Okay, now H is going to be equal to weight divided by rho G pi r squared. Okay, which is exactly what I did here. I just did it in 2 steps. Okay?
Yes.
All right, let's go next one. Let's do another one. Okay, now this is a famous one. This is about the crown. So the king hero asked the goldsmith, the local goldsmith guy, to make him a crown, fancy crown. He gave him a whole bunch of gold. And why don't you do me a crown? And then he came back and the crown didn't seem to be as he liked, so he wanted to know. So the story goes like that Archimedes put the crown on a little rope, and he actually had some kind of, oops. Oh, no, I'm running too far. This is the Niagara. Okay, let me get the pen. So I put a little rope here, and then maybe something like that, and maybe another one, and put some weight here. And then he figured out that the tension F is going to be equal to, where would I put it, 20 Newton. It's they have different measurement units, but in today's metric, that's what it was, 20.9 Newton. That was the force that he had to hold the crown in. Then the biggest problem he had is how to figure out the volume of the crown. So he actually filled it up. So this was filled up. This was filled up. There was no crown. Then he put the crown in, and then the water spilled into that container. This container was a measuring container. So he figured out that the volume, again, in today's values, was 310 centimeter cube. So now, again, you can do it differently. You can say, you can claim that the weight, oh, actually, I put it here. Why do I write it again? The weight of the crown is actually the lift, which is the displaced weight of the displaced water. So rho of the water, density of water, G, and the volume, which is the 310, that one, and the force F, which was going up. So the total weight of the crown is 23 plus Newton, not much more than, so the water was not really significantly much. And therefore, the density of the crown is supposed to be simply rho GV, but then this rho is the density of the metal. Okay, so you take the weight, which is this number here, the total weight of the crown, and divide it by the volume, which you figure out by spilling the water. The G is the G, and therefore the rho, I don't know if he knew about the G because that's Newton, but he had probably something else. And again, in today's algebra, we do that and we end up with 7,880 kilograms per meter cube. If I go centimeter cube, centimeter is 100, it's 10 to the fourth. So it's gonna be 0.7, anyway, 1 cubic decimeter, which is 10 centimeter by 10 centimeter, is going to be, in water is going to be 1 kilogram, and this is going to be 7.88 kilogram if it's steel. That's the density of steel. And if it would be the density of gold, that should be 19.3. So that was mostly iron, cast iron, and kind of plated with gold. So the poor guy didn't survive for too long, as I believe. Anyway, so that's the story. I believe that he ran on the street after he showered because he figured out how to measure the volume. That's what I believe. Because he could do weights, but he could not do the volume. I think that was the Avrika that he was very happy about. Anyway, so this is again about buoyancy. And some people claim that this is how he came up with the rules of the buoyancy. Oh, here's again, one of the most complicated one that I can come up with. And then there's another one which is complicated, but this is more mechanical, but this is the more complicated from our point of view. So we have a balloon. We have a balloon which is floating, and we have the dimensions. Okay, let me go more specific. It's a hot air balloon. Okay, total weight is given. Total weight is given. Temperature is given. Outside temperature, so it's a little bit cold, but it's 290. It's like 7. It's like 19 degrees C. I think it's in the 70s or high 60s. Anyway, density of the air at that particular temperature is given, and the approximate diameter. So we can approximate it like a sphere. All right. So the question is, how much has, again, for those that don't know how the hot air balloon works, there is some kind of a torch here, and it heats up the internal side of the balloon. So inside it's hotter than outside. So I call it T hot. Inside the temperature is going to be T hot. It's completely open, so the pressure in and out is the same. Now, so what are the forces? There is going to be a buoyancy force, which is going to be equal to displaced liquid outside. So we can call that lift this is really the true lift, what we discussed so far. But then we have to minus out the weight of the liquid, which is inside. So actually there is a weight inside. So there's the total lift force is not like this was completely empty, okay? And now we're talking about air, and then the density differences are very small, so we have to pay attention to that. So at the end of the day, this will be the volume, and then the net lift is the difference between the two densities, okay? And that should be equal to the weight, which is provided right here, okay? So now, if we want to be more official, then we look at the ideal gas relation, but the pressure is the same. So we end up with this. Therefore, I go back to that equation here, just rewrite it. So I take the density cold outside, that it's 1, and based on that, the density of the hot is equal to the cold multiplied by T cold and T hot. So this is the correction due to that one. So this is going to be, this is colder, so this is smaller than 1. G, and then the volume. Volume. All numbers are provided. All numbers are provided. The only things which you don't know is this. This is unknown. This is unknown, so we just turn it around, and this is the weight, of course. It's given. So we kind of solve for this, put it here, and here are all the numbers which are known. I plug in the numbers, and D, for example, it's 15 meters. There's going to be 7.5 square pi. G is 9.8. Density cold, we said 122. And then the lift is going to be equal to the weight, okay, which is given here, 275. So that's the number. You solve that, it's 332, which is Kelvin. You have to do it in absolute temperature. And this is 59, it's almost 60, 60 degrees C. Who can help me out? How much is in Fahrenheit? It's pretty hot. 60, it's somewhere in the 140s. Any helper, or should I go to the?
I believe it is around 140, yes.
It's about 140. So it's pretty hot, but it's not going to burn the material that is kind of putting in the balloon. Okay, so I think from a calculation point of view, this is probably the most complicated problem. Can I move on? And those that have been asking questions about exams, and so can you follow something like that? Positive answer, negative answer, anybody?
I could follow this, I think.
Okay, so that's what I'm saying. That's one of the most difficult, because this is the concept. Okay, this is the next one. Let's do the next one. I think this is the last one. I'm going to do it. Again, buoyancy is something very simple. You heard about it in high school. And okay, so now we go to the toilet. Okay, here is the problem. So the toilet has a Niagara, and I'm just kind of coming up with some idealized solutions. So let's say that this floater is half submerged, only half of it. And then what happens is when you drain the water, this thing moves, this kind of valves goes up, and then the flow opens up here and it flows in. So the question is, how high will the volume go for this to stop? Okay, so, or what is the force on the valve? What is the force at that particular point? That's how it is. So everything is given. We have the radius, which is 8 centimeters right here. And this is the condition that we would like to solve. It is at an angle of 15 degrees, but the ratios remain the same if you come here. So the arm ratio is L2 to L1 is very much like it's given here. It's 15 to 5, same thing. So the vertical force is going to be L1 Oh, I just, okay, I did that, all right. So what is the force? The force is the buoyancy of 1/2 of the sphere. So now you're going, if it was an exam, you're going to ask me what's the volume of the sphere, and I would give you this, okay? And it's only 1/2 of the volume, and then rho g, plugging in the number, so it's 7.88 Newton. That's the lift force due to buoyancy here at that point. That's the force. So now we need to figure out what is the force here. She's going to be, of course, larger. So we just take the ratio, which is this distance, which is L1 plus R. So L1 is going to be 15 plus R was going to be 8. I do it in centimeters over 5. I hope I did it right. And then the force was 7.88. And I hope my calculator is correct. And this is the number. This is the answer. So this is the force on that one. Of course, we can have other options, and I can give you the distance here, and ask you how high the container has to be filled up in order for the valve to close. But it's the same principle. So it's just going to be involving more geometry. Okay, very simple. Any more questions on that? You're quiet? Okay, I'll move on. So in principle, we finished hydrostatic chapter, and that's it. And you've seen examples of what I would like you to be able to solve, and that's it. Now, this is an opportunity for me to introduce something which is called stability, which not everybody is exposed to. And it's a very important topic. So here is the situation. You have some kind of a roller, and you go with a rod, and you're pushing it forward. Something happens, and the real roller moves sideways. Then turns out that the more it goes sideways, the force is larger. Therefore, the effect is going to be that, I made this around. So if we define, say, beta, I touched it again. Okay, I'll just go back. I get the pen, okay. So let's say that beta is positive this direction, and M is also positive this direction. So we did a delta beta, which is delta beta, which is positive. And then the result was a delta F, which is also positive, or delta M, the moment, also acting to the same direction. So there is a definition if both of them kind of get it outside. Then this case is this, and we conclude that the derivative dm to the direction, to the same direction is positive, the situation is unstable. So again, you know it from the supermarket cart, if the wheel would face forward, it's not going to stay in the same line, it's going to spin around. Now, let's look at another situation. You're now towing, you're pulling the rod, and then we define beta, positive beta this direction. But if I kick it sideways, the resulting moment will be restoring. We'll try to bring it back. That would be the moment. Therefore, I conclude that the derivative dm d beta is negative. So the conclusion is pretty general. It's general. We can claim that this is a stable condition, stable, and this one is an unstable condition. Okay, so that's why I'm mentioning it now here, because people that design ships, there are some stories about historical about ships, wonderful ships that, what's the name of the Vasa? Anybody heard the story about the Vasa, the Swedish ship? Any student hear that story? Vasa. I don't know how in Swedish they write it, Vasa. It was a beautiful ship and it flipped over in the maiden sailing. So here's a good ship design. Usually some of those ships will have the center of gravity above the center of buoyancy. So the center of buoyancy is at the center of the area, So now what happens if I tilt it this way? I call it phi. But then the centroid actually moves to the right because this would be the volume and it looks like the centroid is here. So the resulting moment is restoring actually, therefore we conclude, hey, it's negative. So this is stable. Now, here's another consideration when things very similar, but it's too narrow. It's too narrow. So here, my picture is not good. It's actually here, but it's still not in the right place. And therefore, the restoring moment is the same direction. This one is unstable. And then usually when people speak about stable, unstable, they always show neutral situation. So if that would be a sphere just floating, it's neutral because it always moves the same. So there's no way to create a difference in the location. So that would be the neutral. Let's see what comes after that. Okay, no, then we already covered the new move. So here I just want to say something else. So any car guys out there?
Yes.
No car guys.
Yes.
Your CG is here. That's a typical car of today. So you're trying to turn or just going somewhere and you hit a curb. Then there's a side slip on these tires, but the arm of the rear tire is larger than the arm of the front tire. Therefore, the car will actually try to stay straight because this is restoring the car. If the CG would be in the back, like in a car, some of the cars, then it actually will try to turn more into try to lose the back. This is called oversteer. So this is oversteer, this is understeer, and it depends on the CG. So now there are lots of Porsche fans over there. What the Porsche guys do, put a bigger wheel here. So to compensate for the shorter moment arm. Okay, so I'm just saying that this principle here has far more important meaning in all kind of other disciplines, and mechanics, shipbuildings, airplanes particularly, and that's it. So that's why I mentioned that particular topic. It relates to floating objects, so there it is somewhat relevant to buoyancy. Okay, we finished this, this chapter. Very, very simple. Let's move on. I promised you that we're going to return to the one-dimensional concept, where we're going to exercise basically the integral form of the continuity or the conservation of mass and momentum. And again, I said that before, and let me just repeat it. What is one-dimensional flow? And I promise you that we'll get back to that later on as well. So if I have some kind of a hose or something, and the water comes out here as a jet, and then the first time I told you there is no slip boundary condition, I tried to convince you the first class. Of course, if you did not forget it, then you believe me now that that particle is at zero velocity. therefore, we must have a velocity profile which looks something like that. So if I claim one-dimensional, then I would like to represent that flow rate with one number velocity, and therefore I assume that the velocity profile is constant, and therefore the magnitude of this arrow here is equal to the average velocity here. So these two are identical for practical reasons, okay? So once I made that, I can continue with that. And now what I'm saying here is that I introduced you the one-dimensional conservation of mass and momentum. However, there is one more tool which everybody quotes and everybody is using, and almost every expert uses Bernoulli law. Bernoulli is not always right, but when things are good, it's very easy, and it's pretty much a one-dimensional tool. So I hope by end of the semester, you'll understand when it's going to work and when it's not going to work. So I will introduce the Bernoulli law, which is very important. So this is going to be the first time that we're going to have some more fluid dynamic oriented development. And I think this chapter is going to be very interesting and very enjoyable, at least in my opinion. So we need to develop the Bernoulli equation. So we're going to have three equations. We're going to have conservation of mass, conservation of momentum, and Mr. Bernoulli's theorem. All right. So, and I mentioned here, there's an easy way and a more complicated way. And of course, I start with the easy way. The more complicated way, we're going to do it later on. I think it will require a bit more algebra, but I actually have a slide here to scare you later on, if you want to, how to do it in a more complex manner. So this is the simple way. Don't be afraid. It's very simple. Okay. So we have a car here. It is going, and the flow goes around it. I'm not really looking at the flow which is very close to the surface, because I mentioned that near the surface the flow stops. So, but I'm just trying to go around the body. There are some streamlines which are going very smoothly. And then we're going to look at some points. We get the pen before this disappears. We're going to look at some interesting points here, A, maybe B, and maybe C. Let me just think about it. A would be the free stream. So it's very much, if the car goes at 50 miles per hour, this is the flow coming at 50 miles per hour. No rocket science here, right? If I look here in front of the radiator, the flow almost stops. So I would think that relative to the car, the velocity is probably close to zero here. And then here, it may be faster because it has to go around faster. So one more time. Let's say you're in a park and you have some trees here. Maybe there's a tree here, another tree here. And now two of you are running. One guy runs straight and the other one runs around here, and then you guys want to meet together. So naturally, this one is running faster, that's why I assume. So that's the same story. Okay, let me be more mathematical. Don't hate me. Okay. So remember the Navier-Stokes equations. If I say that there is no viscosity, so there were the viscosity terms, I throw them away. Okay, that becomes the Euler equation. Then later on, I'm going to say even that it's steady state. So we're going to end up with this. This is and then we said that density is constant. It was a constant. So then we can do that. We put it here, the density here. So now this is a vector form. And if I want to write down the same thing to the x direction, this is the same thing. This is exactly the same thing. And you have that x direction, y direction. Almost immediately, I cross the sign, I say steady state. Okay. Now, what about this force thing? Why don't we just look at some gravitational force? And we said before that the body force, we're really looking at gravity. So this is G, but if I want to put altitude, and H goes to this direction, so I can say the gradient. So what is the force itself is the derivative, okay, which is going to be, well, rho GH, that's going to be the force, okay. So if I do this, then I have to do some hand waving here. So I would like to write down this part. But then I think that let's pick up this streamline, or maybe we can, let's have an easy one. Let's pick up this streamline. And this one is not really turning much, not much friction on it, and it's pretty smooth. So really the key word is that the streamline is undisturbed. It's no friction, no elements that's stopping it. So it goes smoothly. Then I can say, instead of X, I can use a coordinate along the line, which I'm going to call S, little s. So if this is the case, then I don't have side flow, and not to the Y, and not to the Z direction. So these are 0. So I end up with U du dx from here. But instead of X, I said I'm going to use S. And then instead of this one, I take that, because its gradient is d of dx, d dy, d dz. Instead of d of the dx, I take ds. And then the pressure, I always said, what is the gradient of the pressure? Is P over rho. Okay, gradient of P over rho. That's the gradient, P over rho. That's what it is. But rho is constant, so here I put the rho out. Okay, so this is exactly the same thing. Am I convincing you? So that's the only hand waving I have to do. I have to basically claim that this is a one-dimensional flow along a streamline S. This is in nicer words, saying the same thing I tried to convince you with all kind of hand waving. If you believe me, anybody believes me? I need one believer at least.
I believe in you.
I believe you.
Yes.
Okay, one believer. Okay, good. I can move forward. So, all right. Now, so I just repeat that. Okay, let me get the pen. I just repeated that. This is what all the believers believed me. And then I just rearrange it. I put everything on one side. Okay, so I have actually plus GH. I move everything to this side, to the left-hand side. D over ds. Now, U du ds is actually derivative of U squared half, right? This is high school stuff, correct? And it's equal 0 on that streamline, okay, on that streamline. Now, if there are no changes along the streamlines, no friction, nothing, then I can integrate from point 1 to point 2. I call it point A and point B. And I'm referring to that particular streamline shown before. And then if this is true, I end up with this, which is, some people call it energy equation. I don't like to call it energy. I just call it, this is Bernoulli's equation. He says that the body force or gravitational potential, and then the P over rho, and then the velocity square half is equal to constant. Anybody mechanical engineers, you use that as enthalpy, by the way. So you're probably not mentioning Bernoulli, but that's the same thing. Because that would be kinetic energy, that would be energy to pressure. Anyway, I'm not trying to convince you. This is Mr. Bernoulli. He lived till 80, he was 1700 to 1782. Pretty good age on those days that people lived maybe till 50. So again, very good proof that fluid dynamics is a good profession, and I really recommend it for many students because it promises that you very long and peaceful life. Okay, so that's the Bernoulli equation, the one-dimensional, and then the next question is how we're going to use it. Okay, so first of all, I said that it is a constant. So if there is no friction losses in the field, like I'm describing here, then I have to apply it between 2 points. So the principle here is you take that, and if it's a constant, you have to use it between 2 points. So say I applied between A and B, and then air is very light, so I throw away the gravity, and therefore I end up with actually PA minus PB is going to be equal to rho UB square. Okay. So now there is an interesting point here, and I claim that here U is equal 0. If this is the case, because it opens up and the velocity is very close to 0, then I can actually call point A infinity, okay, point A infinity, and then, did I do it right? Oh yeah, I did it the other way around, okay. Then it turns out if I do the same thing, I end up with this relation. So one more time, pressure is probably low because the quantity is constant. Pressure plus velocity square is constant. So if velocity is larger, pressure is slower. So the concept, remember, higher speed, lower pressure. So this is higher pressure when the velocity is 0. So this velocity is 0. And therefore, for that point, assuming velocity is 0, I end up with this equation. This has a very important meaning, okay, because we can claim that PC is called the total pressure. This is the static pressure. And this is the dynamic pressure, which is actually rho U square. This is the velocity. So one more time. You in the car, don't do that experiment at home. This is only for professionals. You take your hands outside of the car. In the palm of your hands, you're going to feel a higher pressure than outside. Then the pressure you feel in the palm of your hand is called the total pressure. The static pressure is the ambient, the prevailing pressure outside. And then the dynamic pressure is the velocity square times density half, which we call dynamic pressure. Okay, I would expect you to remember this very well because this is important. Some people don't understand that. That's very, very important. I have a few more minutes, so let me see what is my next slide. Okay, my next slide is simply a summary. Okay, so here's a summary of the one-dimensional tools. So we said, again, we looked at steady state, and for the steady state for conservation of mass, we had a control volume going in, coming out, and we concluded that because it's incompressible, there's no accumulation, so the mass going in must be equal to the mass go out. Also, we have a good formula of how much is the mass flow rate. So you have to remember that's a formula by itself. The force is going to be the difference between the momentum, okay, in and out, and also a result of the pressure on those surfaces, if there is a pressure difference. For example, if this is a jet engine, there's high pressure here, and therefore the pressure on that surface is going to be higher than the pressure here, which is exposed to the ambient pressure. So this is possible, okay? If I want to use that equation, the continuity, so yeah, I call it continuous sometimes, and instead of rho UA, instead of this one, rho UA, but I take the square out, no square, I end up with the momentum U. And this is a more familiar term of the momentum because it resembles Newton's formula. And then you have to add the pressure in the back, pressure at the front. And then we have a third formula, which is for Bernoulli, which is now, we have to use 2 points those 2 points should be undisturbed. So we can't have a flow going through unless it's completely smooth. So I propose maybe point A and point B, which are not exposed to friction or propellers or anything like that. And therefore we can assume that there's a conservation of energy along this line. I'm saying it because I kind of know that that's what it is, but I didn't completely prove that. Okay, so you have to think that one more time. You can use Bernoulli if there are no losses along that line. Okay, and then Bernoulli is correct. You have a vehicle, okay, and the flow goes around. You can pretty close to that, and go pretty close and ask point A and point B, and you can apply the same rule. But as I mentioned, if there is flow separation here, you cannot have point B here, because now we have flow separation and there are friction associated with that. We'll clarify these things more and more, and then we're going to use that later on. Let me just, okay, I have 3 minutes left. So that's basically end of the class. I just want to shoot forward for a second. So we're going to do examples. There's going to be free jet, but I just want to get here. So there are going to be lots of instruments based on that Bernoulli principle. There is going to be a pitot tube, which we're going to discuss. There's going to be a Venturi tube, and then Venturi tube, and then there's going to be an orifice. These are instruments which are based on the same principle. So this is a very important principle, but we have to understand what it means. And again, we're going to do examples. I'm going to repeat myself a few times, hopefully not boring you too much. Gentlemen and ladies, I think my clock shows me that we kind of finished. Any major questions?
Well, one question, professors. So with the mx m dot u2, like the equation you were showing us with the 1D tool steady state, that's also about thrust, right? Would that be the, okay.
So you can do thrust with that. Yeah, where is that? I can go back. Actually going to have an example. Let me, okay. Okay, I'm going to have an example about a jet engine in the future. And it is exactly that we can calculate the thrust based on the differences and on the pressures. Okay, this is exactly the same formula I showed you. It works here as well. I'm just trying to sell you here a simplification that we can make it easier. That's all. So any more questions? Stop share.
When we submit the homework, do we get like a confirmation email?
Excuse me, I didn't hear you well.
When we submit the homework, do we get a confirmation email or?
No, I don't think the grader will do that. I think that question somebody asked earlier, and my response was that we keep on accumulating those things. And once you accumulate 4 or 5 more, or maybe before the exam, I'll ask the grader to provide me with the list, and you say, hey, I'm Joe, and tell me how many homeworks can you see on the grader's list? So I'll tell you, oh, I've seen all of them, you're good. Or, hey, this one is not there. And they'll say, oh, but I submitted it. So then we try to trace it down and see if it's correct. Okay, sounds reasonable?
Yeah, thank you.
Okay,
Yes.
you're very welcome. Okay, class, thank you very much.